Hey guys, how's everything going? I'm JSer. This has been a long time since I last uploaded my videos. There's a huge, the whole world is about the coronavirus, and I hope you're doing well. Please stay at home and stay healthy. Hope this coronavirus will be gone soon. And this is a very good time for us to stay at home and learn some algorithm problem. Uh, Today, let's take a look at number 84, largest rectangle in histogram. It's labeled as hard. We're given n non-negative integers representing the histogram's bar height, where the width of each bar is 1, like this is 1. Find the area of largest rectangle in this histogram. Okay, so as the example said, the largest one would be this one. Yeah, there might be many rectangles, like this is 2, this is 1, maybe there's a 2 here, and there's just 1, 2, 3, 4, 6, like this, right? So the largest one is double 5 here. If there's a 7, there will be 15. So, well, this, I think for this kind of problems, there always be a tricky version. But before we jump into that one in the real whiteboard test, let's start with the brute force solution. The solution, the basic solution for this one is pretty simple. We find all the rectangles and compare the size, right? Okay, so this first one I'll label it as brute force one. We'll find all the rectangle, so it will be n square to find it, and we need to calculate the area, right? And for that, we need to get the minimum. Say we get, so we need to calculate the rectangle generated by 2 and 5. We need to find the minimum height, which is 1. So this one. So this will cost an extra linear time. So it's actually big O in cubic. It's pretty slow. Let's take out the look at the result. So okay, it's pretty straightforward. Let's just jump into the code. This is the start point of the rectangle, and then let j equals j plus 1, I plus 1, sorry, and this should be, it's the bar itself could be a rectangle, so I'll start with I. J plus 1. So this is the ending point of the rectangle, and then we need to find the minimum, right? And minimum equals, I'll say it start with height I. So for let k equals this time it could be I minus 1 k. And k will jump to j, k plus 1. Oh, I think we have a better one. The time complexity will not change, doesn't change, but we could be faster. We can use the native math, which is main heights slice I plus j plus 1. So we get the minimum, and let's say let the max equals 0. we find the minimum. Well, this is the height of a possible rectangle, and we calculate it with the width, which is j minus I plus 1, right? Yeah, this is the width. This is the input. Okay, now return max. This is pretty straightforward, right? Let's run the code. Hope it works. It works. Not a number. Math max, max 0, main. Maybe I slice. Really? Really? Ah, my bad. There is actually. I think this should be a slight spread operator here. Yeah, let's submit. Of course, it might fail. It might just take too long time. Yeah, time limit, TLE problem. Of course, let's try to improve it. The first idea come to my mind is that because we're checking every possible rectangle, but we were getting the minimum of comparing them over and over again to get to the minimum, right? For like this one, this will be minimum for the rectangle generated by 2 and 5, and also 2 with 6, and we will be compared all and all. It's not a good idea, right? So I'm suggesting that we have a better solution. Is that we check the ending bar of the rectangle and do it in a backward way. Say like we get 2, there's nothing we can do, so its maximum is 2. But for 1, the rectangle ending at 1, we check it 2, it's bigger. Okay, we get the 1. The minimum is 1, so we get 1, right? So that for this, what we're getting is that we're checking for each bar. This will be linear time, and then we will get the minimum, right? And this will be a linear time, and then nothing else. So we can do it in a possible improved. It's actually brute force, but it will be O(n) square, I think. Yeah, let's do it. So it will be check ending bar. For each, this will be the ending bar. Okay, we will start with it and go to j will be bigger than j minus 1. So check it backwards. Let's say we would get 5. The possibility of square ending at 5 will be 5, 1 and 5, 2, right? Yeah, so okay, this is the loop. let's say if it is smaller than it, then for the bar before 1, we don't need to check, right? We need to find someone smaller than 1, right? If it's bigger, I'll say how to say, if the previous one is bigger than 5, it's 6, then it's the same as 5, right? Because it's 6, the maximum will be 2, 5. If it's 5, it's 2, 5, right? So it doesn't matter. It's bigger than it. We only care the smaller one. We will get it. So the general purpose is find the slope downwards. I'm not sure I make this clear. Let's put it the ending at number 6, the bar of 6. We find 5. Okay, it's more than 6. So this is a possible solution. And then we go again. If it's again 6, it doesn't matter anymore. It doesn't matter anymore. We count it as 5. So it will be 3, 5. So the key point is that keep the minimum number, which is smaller than current bar, right? So we say we keep the minimum. Oh, the result is max. Okay, I say smaller equals heights I. If heights j is bigger than smaller, then it is smaller, right? I mean, if it is like 2 is bigger than smaller 1, then it's just smaller. If it's 0, then we can break. So if heights j equals 0, we can break. And if it's bigger than it, then it is smaller. So we update it max. Math equals math max. Max. It is smaller. Keep that in mind. Which is smaller times I minus j with plus 1. Okay. If it's smaller than it, then smaller it's itself, right? Smaller equals heights j, and we will do it again. So we can improve this part. So it's smaller equals math mean smaller heights j, but not this height j must not bigger. It must not bigger. Wait a minute. It's not. Oh yeah, it's right. So, this should work. Actually, we can make it more concise. Yeah. So when we find a new bar to the left, if we keep track of the smaller one, so it will go down and down, and then we calculate the size of the square, and update to the max. Yeah, this should work. Let's say actually this one is n linear, and this only 1, 2 comparison. So I think it's good. So it's improved the complexity. Let's run the code. Let's say heights is not defined. Heights, there's a typo here. Not a number. Oh, 0. I forgot to initialize the max. Submit. This is working. Okay, it's working, but it's only faster than 11% of all the solutions. Let's try and prove that. And generally, I think there will be a tricky improvement which leads to one pass, which is linear. Let's try to find out. So when we doing the improved brute force solution, we're keeping track of the we notice one characteristic of this problem, that if there's a 6 and there's a 5 after it, like this 6 here, 5 here, then this 6 doesn't mean anything, right? Because we only find the smaller one, keeping the downslope. So if that's the case, maybe we could do at the beginning, not in the backward way, but for these 4, we can already keep track of the upward slope and do the calculations, right? So let's say the first, if we find a 2, right? And then this 2 might be the possible solution. So we calculate the size, it's max 2. Okay. And then we made this one. We made this one. This 2 is meaningless. Is becoming meaningless, right? Because if the square contains both 2 and 1, this one will be the minimum. So this 2 could be crashed into 1. So this 2, 1 actually is the same as 1, 1, right? So this is the most important characteristic of this problem. So let's transform this graph into a new one. Okay, so the first one was is 2, and then we made 1, so it will become 1, 1. Of course, when we're crashing down this bar, we will compare it with the final result, 1, 1, right? And then we get 5, and then 6, and now we get 2. For 2, this 6 is meaningless, so it must be crashed, cut down to 5, right? The previous 5 is bigger than 2, so we crash it, and it will become 5, 2. Still, this 5, 2, 5, 2, 5 is bigger than 2. We need to crash it again. So 2, 2, 2. And then we get 3. So the problem becomes very simple. We keep, we keep only the key points, key bar, meaningful bars, and remove the meaningless bars. And the graph finally will become concise as 1, 1, 2, 2, 3. Well, this at last it's this upward slope. We'll cut it down, crash it, and it will become 2, right? And then we crash all to 1, 1, 1, 1, and then finally we can calculate it all. And for this 1, 1, 2, 2, 3, 3. 1, like say 1, 1, 2, 2, 3. This could be simplified into an index and the value, right? This is generally means at the index of 1, 0, we have 1. And from 0, all will be default to 1. And then we find at 2, index 2 here, we got a 2. And then at index 1, 2, 3, 4, 5, 6, which is 5, we have 3. Right? So we don't need actually to keep track of the array. We only need to calculated the size of the square, so we only want to know the width, which the width could be derived from the index, right? 2, 5. So the width would be 2, 5 would be 4. The size would be height, and the previous one, right? So 2. Okay, so that's cool. So let's start. So the final try, maximum. Okay. Now we need to keep track of the key points. So it will be two-dimensional array. So let key points okay. So I'll just remove this part. The key points will be something like index and height. Right? Yeah. So when we are traversing through the array, we find something bigger than it, bigger than the key point, the top of these key points, we push to the new point, right? But how we handle the initial one, we can check by index, or we initialize an empty point, which is something like the bar here. I would call it, the index will be -1, and the value will be 0, because adding this point will do no harm, right? Yeah. Because the height is 0, it doesn't change the maximum, right? The final result. So, okay, let I equals 0. I is smaller than height, I plus plus. So what we do? We will try to find a new point. We will do what? If it is bigger, we will push it, right? If it is smaller, we need to crash it down. And anyway, if it is big, what we do when we crush the bar down, we need to compare the topmost number to this one. If it's, we will crush it down and down until the topmost point, the bar, will be smaller than it. So actually, it doesn't matter which is bigger than it or not. So I will summarize into a separate function called crash. Crash. It's crushing. Crush it down. Maybe maybe I make a mistake, but I'll just keep using the crush. I hides I, which means I will crush the key points, because we're having a new point which is at index I with the heights of heights I, right? Okay, crush. How we handle the crush? I height. If it's bigger, we'll insert a new point. If it's smaller, we need to remove the point, right? Until it's finding the best position, and finally we will insert it. So the new point will be I set it default to index and height, right? This is a new point. And according to our observations, while the top of the key points array is bigger than it, we will need to crush it down, right? Key points length. If it's the same, yeah, it's okay. The same, we could do the same. So it's bigger or equal to height. Crush the top rightmost, I say rightmost key point if it is not smaller. Okay, how we crush it? Why it's simple? Because the point is array of index and height. When we remove it, we remove the possibility of this graph, this bar, starting the square starting from this bar to the index I, right? Let's say we made a 2, we crush 6 to 5, so remove the possibility of this the square from 6 to 2. Yeah, it's simple. So max will be max the top. Oh, wait a minute. We need to compare it. So okay, now I'll say const key top equals key point. First I will pop it. Either way I will pop it. No, I won't. Oh, I don't need to pop it if it is bigger. So this is the top. If this is the truth, if not, I'll say key points push new point. Okay. If it's smarter, yeah, while we could crush, we crush it. So we pop. This will be top 1. This is the height times index minus top 0. We don't plus 1 because we only remove the bar here, not containing this 2, right? We're removing the 6. So we do this while loop again and again. Now we change the 6 to 5. Now we have double 5, right? When we remove it, it means the index of the new point will move here, right? No, we will continue crush until the while loop is done. So we will finally met the point here. We find 1, right? Which means the while loop will not continue. So at that time, we new point updated to 0 equals the where is it? Top is here. New points. Where is it? Wait a minute. 6. We calculated, and now we have 5. We calculated the size. Yeah, I think, oh, I made a mistake. I can safely update it, because if it's smaller, when we're crushing down the 6, I can safely move the index, right? Insert, say it will be moved to 2. Yeah, definitely. Index. No. New point will at least be here, because it's smarter than it. So point index will be top 0. And when everything is done, I think this new point will be here. And we can just insert it. And because this is also inserted, so what just say key points push new point. So at the end, all the bars are how to say formatted or reduced into a beautiful upward slope. And what we do at last, yeah, of course, just as the beginning, just as where what we do at beginning, we insert an empty point, right? We can just insert a new point, which is the I height length. The height will be 0. So when we inserting 0, all the bars will be crushed down, right? Yeah, cool. Let's run the code. One of undefined key points. Well, key points. Okay, let's say let's crush key points index height. Zero, 2, 1, 2, 1, 1, and 2, 5 will be 0, 1. Okay, 2, 5. Okay, 3, 6. It's right. And then we have 4, 2. Okay, we'll have 2, 2. Yeah. And 5, 3. Yeah. And then 2, 2. 5, 3. Yeah, it's right. 5, 6. Yeah. And the key points length -1. It's weird. I don't know why it says cannot read property 1 of undefined. What does it mean? Maybe there's a typo or something, but I don't know. Oh, shit. Okay, finally we get 5, 3. The top is 5, 3. 0, 1. There's a strange thing. Ah, my bad. Yeah. At last we push this point. This is not good, right? Okay, so we find a new point. If it's bigger than it, then we crush. We crush. I think problem comes here. Key point length plus 1. One. This is bigger than then we crush. If not, we push. Key point versus index height. We run the code. Okay, first one we crush this. We just oh yeah, we push it. So and then we find a 1 1. Push it, push it, push it, push it. And finally we say 0 1, yeah, and then 2 5, 2 2, yeah, and then we got 5 3 versus 6 0, and it's 3. Key point means okay, 3 is bigger than 0. We pop it, and then 2 bigger than 0, pop it, 1 bigger than it, pop it, and then 0 bigger than it, pop it. God, we pop through pop all. So if my bad. We pop too much. If key points, I say length is bigger than 1, and yeah, no, it should be here. We pop it and say if there is anything to pop, right? But for this case, we will say length bigger than 1, we pop. Yeah, to keep the entry element. Yeah, we submit. Oh, nice. Now we're faster. Faster than 75% of all the submissions. This will be we take a look. There will be one for loop here, so it's linear time, and then for each crush method, we have a while loop. It seems like there will be big O and square, but actually there's a trick here. You see, for each the key points we generated, like for 0, for this graph, we will generate something like 1 0 2, 1 1 1, right? And then update it to 0 1 1 1 and 2 5 and 2 6 and update it to 2 2 5. You see, for each bar, like for 2 5, it will be checked for how many times? For this 6, it will be checked for once because it's bigger, and then it will not be checked again. For next time it will be checked, it will be removal of itself, right? How can I interpret this? Let's say if you get a 2, if it's bigger than 5, then it will be just be insert a new one, so it will not be checked again if something is bigger than it. If it's smaller, then it will be a removal, right? Even it's same as 5, then it will be removed and replace a new key point, which is just happen to be 5 itself, and the original bar is 2, right? Yeah, this 5, the 5 of 5, this 5 will be removed, which means it will basically check for each bar. You will check at most twice. One is to insert a new bar, or it will be removed, right? If something like there's a how to say 5 and then 7, this 5 will be checked once, and then we say like a 6, the 5 will not be checked. It will first be checked with 7, and then what happened with 7? 7 will be removed, and then 5 will be checked again, and 6 is kept. And then if we get 4, 6 will be removed, and then 5 will be removed, and it will be only 4 there. So for each bar added, there will be stop at one check if it's big, like 6. It will be only one check with 5, or for 2, it will be several checks. But after each check, each bar will disappear. So it's not linear time for n. I have to make a robust proof of this assumption. I don't know, but I suppose that it will be n times some constant, like 3 or 2 or 3. I don't know. So it's linear. According to our result, it's much faster than the previous solution. How can I prove it? If it's bigger, then nothing is checked. If it's smaller, it will remove. Check once, yeah. So check once or remove one, right? Check one, add one, yeah. I know. So if it's bigger, then it will add one bar, right? Here, if it's bigger, a new bar. If higher, say, if a new bar is taller, then will be a new bar there. If it's smaller, they will remove at least one. So for each bar, it will add one, and or remove one bar, but it will insert itself there. So you will add 0. So for all the bars, they will be adding at most. For the worst case, they will add their bar for themselves, right? So each bar, like something 1, 2, 3, 4, 5, 6, 7. Compare ones and add one bar, right? For that cases, they will be removing some bars by one compare, right? So one compare plus one bar, or remove one bar at least. So for the worst cases, add all the bars, and all the bars will be removed at the last cross here. So 1 bar to add 1 bar or remove 1 bar. That will be linear time total. So it will be linear plus linear. So it's still linear time. Yeah, that's a general proof without the formula mathematically. Okay, so I've done this problem. Hope it helps. Sorry, this video may take a little long time because we started with the brute force solution and tried to improve that, and finally got this. I don't know if it's concise or not, but it's indeed faster than the previous 2 solutions. And the key point of this problem is that we find some characteristics of the problem. That the most important part, if a shorter bar is to the right, it makes the taller bar to the left meaningless. So we can improve the graph. How to say? Make it concise and make it easier to calculate. And because we need to keep track of the size, we only need to memorize the index, which is the first element of the point. So we can derive the width directly without looping through. If we keep track other than a key point like this, we will have something like 0, 1, 1, 0, like array, like 1, 1, 1, 2, 2, 2, 3, 3, something like this, right? We need another for loop to check how many 2's are there, right? So actually, this abstraction help us improve the solution by reducing an extra for loop, right? Yeah, so that's the end for this video. Hope it helps. Yeah, see you next time. Bye bye. Take care.